More than 4 billion years ago, our universe came into being. Human history is only a fraction of that time, and in this short span of time, we have come a long way in understanding our universe as we navigate from countless galaxies to the smallest of quantum particles. The more we explore the building blocks of our universe, the more we are surprised. There seems to be more questions than answers. In spite of all the advances in science and technology, we still cannot answer some basic questions. Why are we here? What caused the Big Bang? What existed before the Big Bang? What is the origin of life? Are we a result of evolution? And the most fundamental and intriguing question of all, does God exist? Let us take a look at some of the most advanced theories and scientific facts and try to see if we can answer that question.
Let us begin our journey and take a look at some of the most advanced theories that shapes our belief system.
Stephen Hawking wrote down an astonishing equation. It would include relativity, it would include quantum mechanics, and it would include information. Hawking's rather simple equation brought us a step closer to understanding the relationship with quantum physics and black holes.
When an object crosses over the edge of a black hole, its event horizon, the object enters a realm basically of empty space, of darkness, and it continues to be dragged toward the center of the black hole, toward what we call the singularity, where it gets crushed out of existence. Every object, in some sense, contains information because it contains a very specific arrangement of particles. So where is the information that describes the arrangement of those particles? Where does it go?
Hawking's description of this process was that the energy remains, but the information disappears.
For many years, for decades, people wondered, is Hawking right? Is the information obliterated and disappears from the universe, or is it still there and perhaps can be in some way retrieved?
The destruction of information was counterintuitive, and it didn't match the rest of the things we knew. In all parts of physics, we had a situation where information doesn't get destroyed. So it was a bit puzzling.
This debate furiously went back and forth up through the 80s and into the 90s when people finally began to articulate this new principle, this holographic principle. And what it said is that all the things that were falling inside a black hole were somehow captured in a preserved image at the horizon itself.
So if the information is not lost on the surface, the information is not lost inside because they are equivalent.
All the information about those objects, what they were like in their three-dimensional existence, was preserved or encoded on the surface of the black hole. That's a little bit like a hologram.
Well, that suggests that maybe that idea may apply more broadly to the universe as a whole. Maybe the three-dimensional objects, us, everything in the world around us, maybe all of the information in these objects is carried, is smeared around a distant two-dimensional surface that surrounds us, and we're just in some sense a holographic projection of that distant data.
The holographic principle tells us something quite astonishing. It says that our ideas of volume, of the real world in a sense, might be a kind of illusion.
Here's a way to think about this. Imagine I took my wallet and threw it into a black hole. What would happen? We used to think that since nothing, not even light, can escape the immense gravity of a black hole, my wallet would be lost forever. But it now seems that may not be the whole story. Recently, scientists exploring the math describing black holes made a curious discovery. Even as my wallet disappears into the black hole, a copy of all the information it contains seems to get smeared out and stored on the surface of the black hole, in much the same way that information is stored in a computer. So, in the end, my wallet exists in two places. There's a three-dimensional version that's lost forever inside the black hole, and a two-dimensional version that remains on the surface as information.
The information content of all the stuff that fell into that black hole can be expressed entirely in terms of just the outside of the black hole. The idea then is that you can capture what's going on inside the black hole by referring only to the outside.
And in theory, I could use the information on the outside of the black hole to reconstruct my wallet. And here's the truly mind-blowing part. Space within a black hole plays by the same rules as space outside a black hole or anywhere else. So, if an object inside a black hole can be described by information on the black hole surface, then it might be that everything in the universe, from galaxies and stars to you and me, even space itself, is just a projection of information stored on some distant two-dimensional surface that surrounds us. In other words, what we experience as reality may be something like a hologram.
In his highly successful theory of general relativity, Einstein tells us that energy equals mass, and mass warps space-time. Remember the physics analogy of the trampoline with a bowling ball in the middle? Like that ball, which gently distorts the trampoline's canvas, the sun warps the smooth canvas of space-time, enough to make planets move in curved orbits. A whole galaxy warps space-time much more. The more massive the body, the more warping. But if we could zoom in on the quantum realm, we wouldn't see a smooth expanse of canvas gently distorted by massive bodies. We'd see quantum foam. Quantum gravity models predict that space-time is a seething foam of tiny regions where minuscule new dimensions unfurl and then furl back in on themselves, spontaneously appearing and disappearing with inconceivable quickness. These regions blink in and out of existence like the bubbles in the foam of a freshly poured beer. There's no such thing as empty space. There is only quantum foam everywhere. Such is space-time for a quantum physicist.
For the past 40 years, astronomers have known that something about the cosmos doesn't add up. First in galaxy clusters, and then within individual galaxies, they found that visible matter, stars, gas, and dust, cannot account for the motions they observe. No one knows what this missing mass, now called dark matter, actually is. But studies by NASA's WMAP spacecraft of the cosmic microwave background, the oldest light in the universe, show how much is out there. Dark matter outnumbers ordinary matter by 4 to 1.
Hello and welcome to the HubbleCast. Now, in its very early years, the universe was extremely smooth and uniform. There were no stars and no galaxies, and all of the matter was distributed throughout the universe very, very evenly. Almost perfectly so. But not quite. Even back then, there were tiny variations in the density from place to place. And over time, these tiny fluctuations grew and condensed into a web-like pattern that pervades and gives structure to the universe of today. Formed of vast filaments and sheets of dark matter, this structure is known to astronomers as the cosmic web. Now the trouble is, because it's made of dark matter, you can't actually see it when you look up into the sky. You can model it with computer simulations, but until very recently, it had only ever been observed indirectly.
Astronomers have mapped a giant structure made of dark matter. It extends almost 60 million light-years out from a huge galaxy cluster and is our best glimpse so far of the scaffolding that gives the universe its large-scale structure.
One day, we will resolve the mysteries of the dark matter. But does that make us any closer in understanding why are we here, or does God exist?
As they try to unravel the mysteries of the universe, scientists are coming to an astounding conclusion. To make sense of outer space, they need to understand inner space, the microscopic matter that forms the foundation of everything we see. But shrinking down billions of times into the realm of atoms and subatomic particles takes us into a strange, unexplored world.
When we descend into the microscopic world, we find that it's really weird, and indeed downright bizarre and unbelievable.
The stuff in this universe is far smaller than anything we can see with a microscope, but it holds the key to the cosmos.
We can only understand where we came from if we understand this crazy micro world.
The magic of the microscopic universe begins at about a 10/1000th of a meter, or the size of an atom. Matter behaves so differently at this level that scientists have developed an entirely new set of rules to describe what's going on. They call it quantum theory, and what it says is extraordinary.
This baseball represents a subatomic particle, like an electron or a photon of light, that routinely does all sorts of weird, strange things in the microscopic universe. The subatomic version of this baseball can be invisible, can go through solid objects with ease, can be in multiple places at the same time, and can seemingly go backwards in time and change the past. This means I could throw this microscopic baseball to first base and to home plate at the same time, or change the seemingly predetermined outcome of a play while it's still going on. Now this is the stuff of science fiction, but really we know it to be true, or at least it appears to be true in our quantum world. We get all sorts of weird things happening.
In quantum physics, what happens to an object over here can instantly affect an object over here, and over here could be millions of miles away.
This is how it works. When two subatomic particles interact, they can become entangled. That means their spin, position, or other properties become linked through a process unknown to modern science.
If you then make a measurement of one of the particles, then that instantaneously determines what the behavior of the other particle should be. And when the experiment is done, it's found that indeed the other particle's quantum state is exactly determined once you've made a measurement of the partner particle's quantum state.
That means if a scientist observes one entangled particle and forces it to spin clockwise, the other entangled particle will immediately start spinning in the opposite direction. That seems intriguing, but it's hardly earth-shattering until you consider that the two entangled particles can be separated by billions of light years. And still, the moment you observe one particle spin, you've dictated the other particle's spin.
That's weird, because it may suggest that information has traveled instantaneously, faster than the speed of light, from one particle to another. I don't understand it. I don't know that anyone does. Spooky action at a distance, as Einstein called it.
Firing photons of light through a metal plate with two slits. The light that went through the holes hit a screen behind the plate.
I'm going to demonstrate the results of this amazing experiment with a bunch of baseballs and a barrier that we've set up which has two holes in it. Now, normally in the everyday world, if I throw baseballs through one hole or the other, they'll form a predictable pattern on a screen that we've set up behind home plate. They'll be in one place or the other. Now, let's make that pattern with a whole bunch of baseballs. I'm going to use this pitching machine. Here's the first one. Let's see what happens. Now you see, the balls landed on the screen in two bunches, pretty much along a direct line from each of the two holes. That's natural. That's what we expect. But when we descend into the microscopic universe and use electrons, which are 10 trillion times smaller than baseballs, we get a very different, odd result when we perform this experiment. A pattern that you would expect if these were waves going through both holes at the same time and interfering with themselves. Well, we usually think of electrons as being particles, so how can they exhibit wave-like properties?
These test results were confounding. The electron was a particle before it was fired at the screen, yet it formed a pattern on the screen, as if this single electron had gone through both holes at the same time. Does a microscopic particle spontaneously clone itself in midair? After years of study, scientists still don't know exactly what's happening.
Probably the most magical thing is that in quantum physics, an object can be in more than one place at the same time.
It actually can sense both slits and actually go through and quantum mechanically feel the structure of both slits in the experiment.
Most physicists agree that the math is quite solid and leads to solutions that are undeniable and can be confirmed with experimental measurements. But exactly what is happening and how is a matter of debate.
To try to grasp this amazing experimental result, scientists decided to observe how individual electrons behaved when they went through the double slit. How exactly could a particle go through both holes at the same time?
Scientists got a front row seat to observe the strange behavior of these electrons or other subatomic particles or even photons of light. Doesn't really matter as long as they're small. They didn't just look at where they landed on the screen back there. They also watched the behavior of the particles as they went through the holes. And then they saw something amazing. When scientists were watching the holes, the electrons behaved like particles, forming the baseball-like pattern on the screen back there. But when the scientists weren't watching, then the electrons behaved like waves. They formed a pattern that looked like the interference pattern produced by waves on a screen. That's really strange. What you see depends on whether you're watching or not. If you're watching, you see the particle-like behavior, like baseballs. If you're not watching, you see a wave-like behavior, but not both at the same time.
This was nothing less than astounding. observation seems to change the nature of subatomic particles.
Mysteriously, when we're not looking, things are waves. When we are looking, they look like particles. So even an electron, which seems to us like a particle, has wave-like properties when we're not looking at it.
The fact that when we don't look, the electron appears to go through both holes, but when we do look, we always see it go through one hole or the other, is what we call the quantum enigma.
How could our decision about whether to observe something change how that something acts? There is a technical explanation.
To make an observation, you somehow have to interact with the system. For example, you have to shine light on it, which then bounces off and you observe the light. That's how we can tell that a baseball is here or there. We bounce light off of it. Well, for macroscopic particles, that doesn't disturb them very much. But for microscopic particles, the act of bouncing the light off of the particle changes where it is and how it's moving.
So in the microscopic universe, where photons of light are about the same size as subatomic particles, these photons have a big impact when they illuminate the particles so we can see them. But this doesn't answer the question. Why doesn't the light simply change the direction of the subatomic particles? Why does observation actually change the nature of what is being observed?
The short answer is we don't know. This is the fundamental mystery of quantum mechanics, the reason why quantum mechanics is difficult. Mysteriously, when we look at things, we see particles. Then when we're not looking, things are waves.
This is something we scientists have argued passionately about now for almost 100 years, and there's still no consensus.
However, the double hole experiment's mind-boggling conclusions don't end there. In recent years, technology has allowed scientists to perform a fascinating variation of the test. Its results call into question our perception of time itself.
This is like a high-tech version of the double hole experiment. Electrons are being fired toward a barrier with two holes in it. But the scientists can delay their decision about whether to observe the electrons until after they've passed through the holes, but before they hit the screen. It's as though I'm on a baseball field, and there's a baseball being pitched toward the barrier with the holes in it. But my eyes are closed, so it goes through, and it behaves like a wave. But then, at the last second, before it hits the screen, I open my eyes and decide to observe it.
At that moment, the electrons, in essence, become particles, and seemingly always were particles from the time they left the electron gun.
So it's as though they went back in time to before they went through the holes and decided to go through one or the other, not through both as they would have had they been behaving like waves. That's really crazy.
That's the enigma. That our choice of what experiment to do determines the prior state of the electron. Somehow or other, we've had an influence on it, which appears to travel backwards in time.
One day, we may uncover the secrets of quantum entanglement, or understand how particles behave like waves. But does that answer the questions, why are we here? Or does God exist?
If we could shrink down to about 1/millionth of a billionth of our normal size, we'd enter the world of quantum mechanics. The laws that control how atoms behave. It's the world of light and electricity and everything else that operates at the smallest of scales. Here, the fabric of space is random and chaotic. Rips and tears might be commonplace. But if they were, what would stop a rift in the fabric of space from creating a cosmic catastrophe? Well, this is where the power of strings comes in. Strings calm the chaos. And as a single string dances through space, it sweeps out a tube. The tube can act like a bubble that surrounds the tear, a protective shield with profound implications. Strings actually make it possible for space to rift.
Which means that space is far more dynamic and changeable than even Albert Einstein thought.
Here's the gist of it. For decades, physicists believed that the tiniest bits inside an atom were point particles. Flying around the outside were the electrons, and inside were protons and neutrons, which were made up of quarks. But string theory says that what we thought were indivisible particles are actually tiny vibrating strings.
It's nothing really mystical. It's a really tiny string. It either closes into its little circle or it has endpoints, but it's just a little string.
One of the great attractions of strings is their versatility. Just as the strings on a cello can vibrate at different frequencies, making all the individual musical notes, in the same way, the tiny strings of string theory vibrate and dance in different patterns, creating all the fundamental particles of nature. If this view is right, then put them all together and we get the grand and beautiful symphony that is our universe. What's really exciting about this is that it offers an amazing possibility. If we could only master the rhythms of strings, then we'd stand a good chance of explaining all the matter and all the forces of nature. From the tiniest subatomic particles to the galaxies of outer space. This is the potential of string theory to be a unified theory of everything.
One day, we may be able to make the connection between the quantum world and the galactic world. But does that still answer the question, why are we here? Or does God exist? Now, let us try to take a look at these questions from a very different perspective. Let us look at the evolution theory.
This theory holds that the species on Earth were not created by God, but came into being as a result of processes governed entirely by chance. The founder of this theory was an amateur naturalist named Charles Darwin. Darwin expounded this theory in his book, The Origin of Species, which was published in 1859. Darwin proposed that all species evolved successively from a common ancestor. But how did that first living thing come into being? Darwin did not address this question at all in his book. He was not even aware that this point was one of the biggest refutations of his theory. The primitive understanding of science in his day assumed that life had a very simple structure. According to a theory called spontaneous generation, which was popular since the medieval age, it was believed that living things could easily arise from non-living matter. It was commonly thought that frogs spontaneously arose from mud and bugs from food leftovers. And some curious experiments were designed to prove these theories. The theory argues that first, the unicellular living beings were formed, which then in hundreds of millions of years turned into marine invertebrates and fish, respectively. These fish later had supposedly emerged onto land, and turned into reptiles. The story goes further and says that birds and mammals evolved from reptiles. For this claim to be true, there ought to have been numerous intermediary species, linking one living species to another. For instance, if reptiles truly had evolved into birds, then countless half-bird, half-reptile creatures ought to have lived at one time or another. And these intermediary creatures ought to have incomplete, half-developed organs. Darwin called these hypothetical creatures transitional forms. He knew that in order to support his theory, the remains of such intermediate forms had to be found in the fossil record. In The Origin of Species, he wrote, "If my theory be true, numberless intermediate varieties linking most closely all the species of the same group together must assuredly have existed. Consequently, evidence of their former existence could be found only amongst fossil remains." However, Darwin was aware that the fossil record did not contain any of these hypothetical intermediate forms. This is why he devoted a special chapter to this in his book and posed these troubled questions. Why, if species have descended from other species by fine gradations, do we not everywhere see innumerable transitional forms? But as by this theory, innumerable transitional forms must have existed, why do we not find them embedded in countless numbers in the crust of the Earth? Darwin had supposed that such transitional forms would be discovered when the fossil record was inspected more carefully. Subsequently, evolutionists that followed him examined geological layers all around the world for 140 years and looked for these missing fossils. All these efforts ended with great despair. The transitional forms imagined by Darwin remained just that, figments of imagination. English paleontologist Derek Ager admits this fact, though he is an evolutionist. The point emerges that if we examine the fossil record in detail, whether at the level of orders or of species, we find over and over again, not gradual evolution, but the sudden explosion of one group at the expense of another. The oldest stratum of the Earth in which fossils of living creatures have been found is that of the Cambrian, which has an estimated age of 500 to 530 million years. In strata older than the Cambrian, no fossils of any creatures except a few unicellular organisms are to be seen. In the Cambrian period, however, many diverse species appear quite abruptly. More than 30 invertebrate species such as jellyfish, starfish, trilobites, and snails emerge all of a sudden. These living beings have complex body systems, such as the circulatory system, and also very complex organs. For instance, the eye of the trilobite is made of hundreds of honeycomb-like cells, each having a double lens system. It is a wonder of design. This is the first eye that appeared on the Earth, and it definitely refutes the Darwinist claim that life evolved from the very primitive towards the complex. Moreover, the honeycomb eye structure of trilobites has survived since 530 million years without a single change. Modern insects such as bees and dragonflies have the same eye structure as did the trilobite. According to the theory of evolution, species must have evolved from pre-existing forms. However, there is no other complex life form known to have existed before the trilobites and other species of the Cambrian period. The Cambrian species came into existence all of a sudden, without any ancestors.
After looking at all these advanced theories, the question is, are we any closer in answering the question, why are we here? Or does God exist? Maybe science can't answer that question. Maybe it's not meant to be answered using science. From looking at the complexities of this vast universe and the complexities of the quantum particles, one cannot say that the creation was a spontaneous accident, but rather a well-designed machine created by a very intelligent designer, whom we refer to sometimes as Mother Nature or God.
وكانتا رتقا ففتقناهما وجعلنا من الماء كل شيء حي أفلا يؤمنون.
Have those who disbelieved not considered that the heavens and the earth were a joined entity, and we separated them and made from water every living thing? Then will they not believe?
وجعلنا في الأرض رواسي أن تميد بهم وجعلنا فيها فجاجا سبلا لعلهم يهتدون.
And we placed within the earth firmly set mountains, lest it should shift with them, and we made therein mountain passes as roads that they might be guided.
وجعلنا السماء سقفا محفوظا وهم عن آياتها معرضون.
And we made the sky a protected ceiling, but they from its signs are turning away.
وهو الذي خلق الليل والنهار والشمس والقمر كل في فلك يسبحون.
And it is He who created the night and the day and the sun and the moon. All heavenly bodies in an orbit are swimming.
وما جعلنا لبشر من قبلك الخلد أفإن مت فهم الخالدون.
And we did not grant to any man before you eternity on earth. So if you die, would they be eternal?
كل نفس ذائقة الموت ونبلوكم بالشر والخير فتنة